Sliding window maximum is a popular but difficult LeetCode problem asked by both Google and Amazon in interviews. The description is as follows. You are given an array of integers nums, and there is a sliding window of size k, which is moving from the very left end of the array to the very right. You can only see the k numbers in the window. Each time the sliding window moves right by one position. And you want to return the max sliding window. Now, it doesn't really define what the max sliding window is, but you can kind of tell what it is from the example. So if you look at example 1, you can see you have this nums array, and then you have a window of size 3. And then what you do is you iterate over all the possible windows, and each window has a max. The first one is 3, the second one's 3, third one is 5, etc. And you want to return the list of all of those maxima. Now, the first step we should take is in finding a brute force solution. We don't care about runtime or memory used. We just want a simple, although often inefficient algorithm to act as a baseline for us. Sometimes this is the best that you can come up with, but at least it is something. It's better than the nothing you might obtain if you try to chase an optimal solution without laying the foundation first. So to brute force this problem, we can use two nested for loops. So the first thing we'll do is we'll let n be the length of the nums list, and we'll initialize variable max list, which would be what we'll return at the end. The first for loop is going to iterate through all the windows, specifically the left endpoint of all the windows. So the first window has left endpoint 0, and the last window will have left endpoint n minus k, because the last window will be n minus k, then n minus k minus 1, n minus k minus 2, up to n minus 1, which is the last element of the array. So in this range here, we want to go up to n minus k plus 1, because Python, it will not include the right bound. If this is unclear to you, go ahead and pause the video and make sure that it is clear before you continue. So the first thing we'll do, given we're looking at a specific window, the first thing we'll do is we'll set the current max to the left endpoint, and then we'll loop through the elements of the window, the k elements of the window, and repeatedly update this curmax variable. So we start at index I, and then the final element, the right endpoint of the window will be I plus k minus 1. So we'll go up to I plus k in the range here. And we will just repeatedly update the maximum. This is a very common line that you'll see in just encoding in general, this updating the max. So make sure that you're pretty familiar with how it works, because you'll see it a lot. Then at the end of this whole process, curmax will be set to the max of the window, of the ith window, and then we will just append on curmax onto the max list. And finally, once we go through all the windows, we will return the max list. And if we just run the code on the test cases, so we're just looking at this one test case, but luckily it works. And then if we use the example test cases, we can see that this solution does indeed work. Now, this solution, it's okay, but it's not very efficient. So, in fact, it's going to be O of nk. O of nk. Now, the way that we get that is that we have two for loops. The first for loop will be O of n. Okay, so because it really, to be totally exact, O of n minus k, but we're assuming k is less than n or much less than n, and we always take the upper bound for that. So the first for loop, O of n. This inner for loop will be O of k, because we're always iterating through the k elements of the window. So O of n times O of k gives an O of nk solution. So what we know is that we can do, we can at least do O of nk, and then at best, we can do O of n. The reason is that this max list is n minus k elements long. It's about n elements long. So, the most optimal solution is still going to require at least n operations. So we know that we're aiming between O of n and O of nk. Some possible candidates include O of n and then O of n log n, or maybe O of n log k. Now, the log ones will appear in situations involving like sorting, trees, or divide and conquer. But in this case, we're going to shoot for the we're going to shoot for the best of those choices, O of n, which is actually attainable. Let's take a look at this example. To find the max of the first window, we do it by our standard method. We just iterate through the elements and pick out the max, and it's 6. There's an important improvement we can make, though, when iterating to the second window, 4, 6, 5, 2. We know that 6 is the max of the first window, and it's also in the second one. And the only element that we actually add to the second one is a 2. So we know that our max, if our max is 6 in the first one, then it's also going to be 6 in the second one. The idea is that if we know the max of one window, then we can find the max of the next. So we'll keep track of a Kermax variable, and then we will update it by comparing it with the new added element. So when we go from B to C, we compare our Kermax 6 with our new element 7. 7 is higher, and then we set Kermax to 7. This strategy seems like it works, but we will run into a problem, and it happens when we go from F to G. Our max 7 will fall off the left end of the window, and so we have no idea what the max is of this list. Now we could iterate through again, starting from scratch, find the max being 6, and continue, but this is inefficient, and there's something better that we can do. What we should notice is that we need to keep track of not only the max element in the list, but also the second highest element, the second max. And so what we can do is if Kermax falls off the left end, then we can set Kermax to that backup value. But once again, there's a problem with this, which is that once we use our backup, we no longer have it. So once we set Kermax to second max, we don't have another second max variable that we can use as a backup later. So then we need to keep track of a third max and a fourth max and a fifth max. And all of this leads to the big idea for the optimal solution, which is to keep track of a list of maxes, which I will call PFM, which is an acronym for potential future maxes. Let's take a look at an example window in a very long list. The first element of PFM should naturally be the highest element of this list, or 9. Now you may think that 8 is the next potential future max because it's the second highest element. But there's a problem here. Think about the idea behind potential future maxes. Could 8 potentially be a future max? Well, the issue is that every future window which contains 8 will also contain 9. And so it's not possible for 8 to become the max of a future window. It will always be overshadowed by the higher element 9 here. Is that a positional disadvantage? Because it's going to fall off the left end first. If instead the 8 was positioned after the 9, like this, then once 9 fell off the left end, it's possible that 8 could be updated to the future max. So then the question is, what is the second element of PFM? You may think it's 5 because once 9 falls off the left end, 5 could become the next max. But the problem here is that this 6. The 6 overshadows 5 for the same reason that 9 overshadows 8. It's bigger, right? And every window which contains this 5 will also contain this 6. So 5 could never become a future max. This is where the idea of PFM begins to take shape. The first element is the overall max, or 9. The next element is going to be the highest element after the overall max, or 6. So this is the highest element after the overall max in this subwindow. Then we apply the same logic. Once 9 and 6 both fall off the left end of our windows, 4 could replace them. So the third element of PFM is 4. And then once 4 falls off, once 9, 6, and 4 have all fallen off, 3 could replace them. So the fourth element of PFM is 3, and then the fifth element of PFM is 1. Because once 9, 6, 4, and 3 all fall off, it's possible that 1 could be the max of this distant future window. It's important to note that in the actual implementation, PFM will be a list of indices of the potential future maxes instead of the values themselves. So for our example that we used, the maxes are 9, 6, 4, 3, and 1. But we won't keep track of this. We'll actually keep track of the indices of these maxes. If we say that 2 is at index I, then 9 would be at index I plus 3, and then 6 at index I plus 5, and then these would be the indices of 4, 3, and 1. And the reason that we do this is, well, for a couple reasons. The first is that we need to know the indices to know when one of these maxes falls off the left end of the list. Just having the values doesn't tell us anything about position. The second reason is that we can easily get the values from these indices. So all we're doing here is giving ourselves more information to work with at no cost, and that's always a good thing to do. Well, usually a good thing to do. So with this in mind, let's go ahead and begin writing our code. The first thing that we'll do is just let n be the length of nums, and then we'll set PFM to be an empty list. Then we're going to write a for loop which iterates through the right endpoint of the window, and this is going to iterate through all of the indices. I'll explain why just now. So we're going to think about this in two stages. The first is the construction of PFM, and the second is the actual updating and sliding of the window. So in the construction phase, all we're doing here, if you look at this, all we're doing is expanding the right endpoint, but we're not changing the left. Then when the window becomes the right size, we start to slide it. So you can see here, right is 0, right is 1, right is 2, right is 3. Then finally when right is 4, that's when we actually start to slide things. So again, the first case is when the construction phase, when right is less than or equal to k minus 1. Let's go ahead and take a look at an example to see how we should handle this. So let's say we have some beginning of a list that looks like this. So the maxes would be 5, 4, and 2. But the actual PFM that we track, the indices, would be 1, 3, and 4. Next, we're going to expand this window to include the 3. First thing to notice is that this 3, this new element, will always become a part of the maxes, no matter how small it is. The reason is that once all of these elements fall off, because we don't know anything about these future elements, or we're not looking at them at all, 3 could be the highest among them. So because we know that the next element is always going to be put a part of the maxes, the question is, where do we put it? Once the 3 gets added, this 2 becomes completely useless, right? The 2 is at a positional disadvantage. It's overshadowed by the 3. Any future window which contains this 2 will also contain this 3. We talked about this before. Now, the 4, though, is still safe because it's bigger than the 3, even though it falls off earlier, right? So what the end result is that maxes becomes 5, 4, 3, and then PFM becomes 1, 3, 5, because 5 is the index of the 3. And you can see how this maintains the same property that we were talking about earlier, where 5 is the overall max, 4 is the max of this subwindow, and 3 is the max of this subwindow. So to generalize the idea behind this process, what we do is, with this new element, we compare it, starting at the very end of PFM, we compare it to the lowest maxes. If this new element is bigger than one of those lowest maxes, so 3 is bigger than 2, then we're going to pop off this max because it comes earlier and it's smaller, so it's totally useless. Then, once that process ends, we hit an element which is higher, in this case 4. We append on that right index, that new element index. So, while nums of right is greater than or equal to nums of PFM of -1. So this looks a bit weird, but remember PFM is indices. PFM of -1 is the last max, the index of the last max, and then nums of that will give us the actual value. And so while this is true, we pop off an element from the end of PFM, and then once this first becomes violated, nums of right is less than one of the maxes, we're going to append on the right index. Now, there's a couple things to note here. The first is that this is a greater than or equal to, and not a greater than. Now, this isn't crucial, so I wouldn't sweat it, but the reason is that even if the new element, so let's say the new element was 2, even if it's equal to one of these maxes, this earlier max is still useless. Like, we'd still pop it off because it's not needed. We have the exact same thing later. Secondly, we need to be careful about a couple corner cases. So here you notice that we access the last element of PFM. So a natural question to ask is, what if PFM becomes empty? And that is possible. So if this new element was 9, for example, then all of these maxes would get popped off. And then in the last call, when we try to access PFM of -1, that will return an index error. So we need to make sure that PFM is not empty. The second phase of this process is the updating PFM / actual sliding window phase. So this is going to look very similar to the construction phase, but the left endpoint of the window is going to move as well, and that's going to complicate things just a little bit. So the first thing we do is the exact same as what we did before. We're going to add the new element of the window to PFM and put it in the correct position. And the next thing we need to do is check whether any of the maxes have fallen off the left end. Because the maxes, or because PFM, the indices are strictly increasing. So the second max comes after the first, the third max comes after the second, etc. Then all we need to do is check whether the first max in the list, or the overall max of the whole window, has fallen off the left end. If the right endpoint is right, then the left endpoint will be right minus k plus 1. If this is unclear, I would go ahead and plug in some numbers, play around with it, and convince yourself that it's true. So if the left endpoint is right minus k plus 1, we want to check whether PFM of 0 is less than right minus k plus 1, whether it's no longer part of the window, it's before the left end. If this is the case, then we will pop the first element off of the list. Finally, because we're looking at actual windows in this sliding phase, we're going to add on the max of the window that we're looking at. And the max is just PFM of 0. So what we can do is make a max list variable, and then we can say max list equals, or max list.append PFM of, nums of PFM of 0. And at the end of this, we will return max list. So let's run the code. Now you'll see that we got a wrong answer. The reason is that I actually made a mistake previously. The construction phase, I said if right was less than or equal to k minus 1. But if right is equal to k minus 1, then we have a window from 0 to k minus 1. That's a legitimate window of size k. So really the construction phase is when right is less than k minus 1. And this slight modification should give us an accepted solution. All right, so that works. Now there's a couple things we can do here to improve the efficiency and improve the simplicity of the code here. So first thing you should notice is that these two code blocks are the exact same. So in the if statement. So we can just pull it out of both of them and write it at the top. Then all we need to do is check whether right is greater than or equal to k minus 1. And if it is, then we'll do all this extra stuff. Second thing we can notice is that pfm.pop0, this is a pretty inefficient method because whenever you remove the first element of a list, it's always going to be O of m if m is the length of the list. So to fix this, what we can do is let PFM be a deck. And so instead of pop of 0, we can just use pop left, and that will actually be an O of 1 operation. And so this should hopefully improve the efficiency a little bit. So here it says our runtime is 1792 milliseconds. If we instead submit this solution, we can see it improved it a little bit, and it's faster than 95% of the submissions. Lastly, remember what we were chasing? We were chasing an O of n solution. So let's verify that this is indeed O of n. This overarching for loop is going to give us n operations. So we need to make sure that everything inside here is a constant number of operations, or at least constant on average. Now you may think that this while loop is going to complicate things, because obviously from index to index, this is going to be non-constant. But if you think about it, in total, over the whole process, every index gets added on, and then at some point later popped off. So in total, there's a max of 2n operations resulting from all of these while loops. And so that's O of 2n, which is just O of n. That's not going to mess up our O of n goal. Then the second part, this if statement, this is just a basic check, These are all O of 1. And so in total, we have verified that this is indeed an O of n algorithm. So that is the solution to sliding window maximum. It's a very tough problem, but hopefully not only do you understand the solution, but you understand how you could actually think of it. And this is a very important component that is often overlooked when reviewing solutions. So whenever you review a solution, not only do you want to understand the algorithm, but more importantly, you want to understand how you could actually get there. What is the motivation for obtaining that solution? Unfortunately, whenever solutions are written in a lot of online forums, including the LeetCode forums, that is not said. Someone will just post a solution and they'll give no context as to how they actually thought of it. So a lot of times you have to do the hard work of, once you understand the solution, sitting down, thinking deeply about it, and thinking about how you could actually get there by working backwards and such. So hopefully that was informative and useful. Make sure to smash like and subscribe, and happy LeetCoding.